Welcome to the Deep Dive. Today we're tackling, well, a giant of popular science.
We're looking at Stephen Hawking's 1988 bestseller, A Brief History of Time. You know, the book everyone had on their shelf.
Exactly, but maybe didn't quite finish. Our mission today is to kind of give you the shortcut.
Right, to distill those huge scientific and philosophical ideas that Hawking managed to bring into, well, everyday conversation. Things like black holes, relativity, quantum mechanics.
He had this amazing knack for simplifying really complex stuff, and he tackled the biggest questions, didn't he?
Absolutely, the core ones. Where did the universe come from? Where's it all heading?
And that mind bender, does time itself have a beginning or an end?
Yeah. And to even start answering those, Hawking had to lay some groundwork. First, defining cosmology itself.
Which is the study of the universe, its origins, how it's built, and its ultimate fate.
And crucially, that the universe isn't static. It's dynamic, it's evolving. That's key.
That starts with Einstein, of course. But Hawking really made Einstein's ideas accessible. We hear relativity all the time, but what's the big takeaway he drove home?
It's really about ditching the old idea of space and time being separate, fixed things, like a stage where things happen. Hawking explained they're woven together into this single thing, space-time, a four-dimensional fabric.
And the crucial part is that this fabric isn't just a backdrop, it's active. It can, stretch and warp.
Exactly. And that warping, that curvature, that's what we feel is gravity.
Right. That blew my mind the first time I really got it. We learn gravity is a force, like magnetism or something.
But it's not. Hawking clarified that it's the geometry of space-time being bent by mass and energy.
Like putting a bowling ball on a trampoline.
Precisely. The dip it makes is the gravity well. Planets orbit the sun not because they're being pulled by some invisible rope.
But because they're following the curves in space-time that the sun creates.
Yes. And that's why gravity affects everything, even light. Light has no mass, but it still has to follow the contours of space-time.
Okay, so if gravity is space-time curvature, where does it get really extreme?
That leads us straight to black holes, the things that made Hawking world famous.
Before him, the picture was pretty simple, right? Cosmic traps, dead ends.
Yeah, defined by that central point, the singularity, infinite density, and the event horizon, the point of no return.
Cross that line, and you're gone from our universe. Basically, cosmic vacuum cleaners.
But then Hawking brought quantum mechanics into the picture, right at the edge of the black hole. And that changed everything.
This is the Hawking radiation part.
That's the one. It was a shocking idea. It turns out black holes aren't perfectly black. They glow faintly.
How does that even work? Does stuff leak out from inside?
Well, not exactly from inside. It's weirder. Quantum mechanics says empty space isn't truly empty. There are pairs of virtual particles, a particle and an antiparticle constantly popping into existence and then annihilating each other.
Okay, like a constant fizzing at the quantum level.
Sort of, yeah. Now, imagine this happening right at the event horizon. It's possible for one particle of the pair to fall into the black hole, while the other escapes just outside the horizon.
And the escaping one? That's the radiation.
To an observer far away, yes. It looks like the black hole itself is emitting particles. And because these particles carry energy away...
The black hole loses mass. It shrinks.
Exactly. Over incredibly long timescales, but yes. Black holes can evaporate. They're not eternal prisons after all.
Whoa! Okay, but wait. If a black hole evaporates, what happens to all the information about the stuff that fell in? You know, the star, the spaceship, whatever. Physics says information can't just be destroyed, right?
You've hit it. That's the black hole information paradox. It's a huge problem that Hawking himself kicked off.
So general relativity, which describes the black hole, seems to say the information is lost forever inside.
Right. But quantum mechanics, which describes the evaporation, insists information must be conserved somehow. It can't just vanish from the universe.
So reconciling those two, that's the core conflict.
It really is. Hawking radiation is like ground zero for the biggest challenge in modern physics. The Great Unification Challenge.
Trying to merge the two main rule books for the universe.
On one hand, you've got Einstein's general relativity. Smooth, geometric, describing gravity and the large-scale structure. It's deterministic, predict where things go.
And on the other,
quantum mechanics, the world of the very small. It's all about probabilities, uncertainty, discrete packets of energy, much fuzzier.
And they both work incredibly well in their own domains. Relativity for planets and galaxies, quantum mechanics for atoms and particles.
Perfectly. but try to use them together, where things are both very massive and very small, like the center of a black hole or the very beginning of the universe, the Big Bang.
The math just falls apart. You get nonsense answers like infinity.
Exactly. Infinities in physics usually mean your theory is breaking down. It's incomplete.
So the ultimate goal, which Hawking highlighted in the book, is finding that single theory, a theory of everything, or TOE, that works for both the big and the small.
Right. Things like string theory, which he touches on, are attempts at this. The idea that maybe fundamental particles aren't points, but tiny vibrating strings, and their vibrations determine what particle they appear to be.
Now, we know from reviews that some later parts of the book, despite Hawking's clarity, really threw readers, specifically imaginary time. What even is that? Why did he need it?
It sounds mystical, but it's really a mathematical technique, a clever trick, you could say.
Okay.
If you run the clock backwards using normal, real time, the universe collapses down to that Big Bang singularity, that point where our physics breaks down.
The messy beginning.
Right. Hawking realized that if you swap real time for a mathematical concept called imaginary time, it involves the square root of -1, but the details aren't crucial. The singularity can just disappear from the equation.
It smooths out the starting point.
Exactly. In imaginary time, the universe could be finite, but have no boundary, no edge, like the surface of a sphere. It has a finite area, but no starting or ending point you can single out.
So it allows the universe to be described as entirely self-contained without needing a specific moment of creation outside the laws of physics.
That's the implication. It makes the universe potentially understandable purely through science without invoking anything external. Yeah, conceptually it's tough. That's why people found the book, as one reviewer put it, maybe more inspiring than fully understandable.
Which isn't necessarily a bad thing. It sparks curiosity. Okay, let's shift to those big philosophical questions. The universe's ultimate fate. What did Hawking lay out as the possibilities?
It basically came down to how much stuff, matter and energy, is actually in the universe, its overall density.
Okay.
Option 1. If the density is below a certain critical value, the expansion we see now will just keep going forever. Galaxies will get further apart, stars will burn out. Eventually, a cold, dark, empty state. The big freeze.
Grim. What's option 2?
If there's enough density, then gravity could eventually overcome the expansion. Everything would slow down, stop,
And then fall back together.
fall back together, yes. Faster and faster, hotter and hotter, until the entire universe collapses back into an infinitely dense point. A big crunch. The opposite of the Big Bang.
Though current observations lean towards expansion forever, right? Maybe even accelerating.
Yes, current evidence points that way, towards accelerated expansion driven by dark energy. But Hawking presented both possibilities as the logical outcomes based on the physics known then.
And exploring these fates leads directly to that ultimate question. If we find a complete theory of everything, one that explains why the universe is the way it is, does that leave any room for a creator? Or does it make one unnecessary?
That's the nerve he touched. Hawking famously said that finding a toe would be the ultimate triumph of human reason, for then we should know the mind of God.
Which sounds spiritual, but his argument was more that a complete scientific explanation would leave no gaps for a divine intervener to fill.
Exactly. It suggests that the universe might be entirely governed by physical laws that we can, in principle, discover. Whether that excludes a creator is, of course, a huge philosophical debate he ignited.
And that's why the book was such a landmark. It wasn't just physics, it was cosmology forcing us to think about our place, about existence itself, through a scientific lens.
It really showed that science and philosophy aren't separate pursuits. They feed each other. Science gives us the how, but it constantly pushes us towards asking why.
So let's boil it down. If someone listened to this deep dive, what are the absolute key takeaways from a brief history of time, the core lessons?
Okay, first, time isn't separate from space. It's part of the cosmic fabric itself, space-time. And it's dynamic, it can bend, stretch, slow down.
Right. Time is physical. Second.
The universe is constantly changing, it's evolving. From the Big Bang through star formation, black hole evaporation, it's never static. There's no fixed, perfect state.
Got it. Third lesson.
Keep questioning. The fact that we still can't unify relativity and quantum mechanics shows our understanding isn't complete. That drive to unify, that curiosity, is what pushes science forward. Knowledge always has further to go.
Makes sense. And the last one feels the biggest.
Humility, maybe. Understanding the sheer scale and complexity and the laws governing it all. It doesn't have to diminish the wonder. It can actually enhance it.
That idea of humility before the cosmos, realizing how small we are in this vast, evolving picture.
It should spark both wonder, absolutely, but also maybe a sense of responsibility.
Okay, so that brings us to the final thought for you listening right now. If we accept that the universe operates according to discoverable universal laws stretching across billions of years and light years, how does knowing that framework affect the meaning you find in your own very finite, very local existence?
Does understanding the immense scale make our everyday actions feel less important? Or perhaps, does knowing the intricate rules make responsible action within those rules more significant?
Something to think about as you move through your own patch of space-time.